Welcome, everybody. My name is Sander Heeman. I'm going to present MonetDB X100. It will also include some demo and the talk. And a joint work with Marcin Zukowski, who was here recently as an intern, Arjen de Vries, and Peter Bons. Okay, so let me give an outline of the talk. I will start with a short introduction on what we're going to do, what is IR on top of a relational database system. Then I'll explain the basic architecture of MonetDB X100, which is our experimental database kernel that we develop, and mainly the two key characteristics, which are vectorized in-cache processing and the storage engine. This will mainly be about compression. And I will end with some experiments on the TeraByte TREC on top of X100 database kernel. So at CWI, we conduct a lot of research into hardware-conscious database architecture, so how we can optimize database architecture to utilize modern hardware correctly. And yeah, this with the goal to process query-intensive workloads over large data sets efficiently. And one of the areas where this is important is information retrieval, large-scale information retrieval. And that's what this talk will focus on. So let's, again, repeat the highlights of MonetDB X100. The first one is a vectorized query engine. This is to maximize the CPU utilization and also optimize for the CPU cache. I will quickly explain how this works in a couple of minutes. And after this, I will explain the transparent lightweight data compression that is built into X100 to maximize I/O bandwidth and to increase buffer manager capacity. So what are we going to do? We're going to do keyword search on top of a relational database system. Well, what does it involve? Given that you have an inverted file with the database relational schema as defined on top, so the TD table with term ID, doc ID, and score columns, we're first starting with two range selects to select those parts of the index that correspond to our two keywords, our two search terms. Then this returns doc ID score columns, two columns which we merge join on doc ID to get the Boolean end of the search terms. Then we perform a projection to add the scores per document, add the scores for each term. And we perform a top end to select the top n ranked documents as the most relevant. So that's not really hard, but the hard part is in how to do this fast as a custom IR engine, which is generally hand-coded, and yeah, all the inverted list processing is just coded in C, C++, so that's often very fast, and we want to approach this using generic relational technology. Well, one of the key ingredients to this is to vectorize the database engine. So our MonetDB X100 kernel employs a standard relational engine based on the Volcano iterator pipeline. You see an example of a query plan on the left in the figure. So the two range scans you saw in the query, merge, join, project. But the main difference is that the parents next calls on the child to retrieve tuples through the pipeline. But traditional database systems return a single tuple at a time, and we return a vector of tuples or a collection of column vectors. So a column vector is just a simple array with, let's say, 1,000 values from a single column, and a collection of these to be able to forward multiple columns. And the advantage of this is that we significantly amortize function call overheads. So we have a function call now at granularities of these vectors, so per 1,000 tuples. And furthermore, operators are now implemented as loops over arrays, and this gives a lot of opportunities for compiler and CPU-based optimization. So CPUs can exploit data parallelism, as can the compiler. And furthermore, the vectors are still small enough to fit the CPU cache. So while this plan is executed, as the vectors flow through the operator pipeline, they stay within the CPU cache. So let's demo, I hope, the impact of vector size. Let me check. It's already open here. So first we're going to run a query with a vector size 1024. Oh, please take a moment to read the right side. We have the TeraByte TREC collection, 25 million text documents, almost half a terabyte. And you see the size of the indexes in compressed and uncompressed form. I'll get back to compression later. We're running on a mid-end server with a 10-disk RAID and single 3 gigahertz Xeon and 4 gigs of RAM. So first we run it on top or with a vector size of 1024. It executes in 323 milliseconds, you see. But this was still on disk resident data. To make the comparison against vector size 1 fair, we're going to execute it again. And in memory, it only takes 40 milliseconds. And please note, in the right, you see the profiled operator tree. You can see that on a per tuple basis, we only need a couple of CPU cycles. Now let's change the vector size to 1 to simulate a traditional database engine. We see that the execution time goes up considerably, and the explanation is on the right. We were first in the order of 10 cycles per tuple, and it's now 600 to 800 cycles per tuple for the most important operators in our plan. But you cannot do it too much. If you increase the vector size too high, it will be counter-effective. As you can see here, we see this curve. We see the execution time of a query as a function of the vector size. At vector size 1, it's slow. It goes down, down, down. But after a while, it starts going up again. This is because if the vector size is too big, results will not fit the cache anymore as they propagate between the relational operators. So we have to materialize intermediate results in main memory, and this starts to become an overhead. And we can see that there is an optimum, and that's what we try to achieve in X100, and it's close to a hand-coded C program. But the problem that occurs is that MonetDB X100 becomes fast. It's 10 to 100 times faster often than most relational query processing engines, and therefore it becomes extremely I/O hungry. And we try to tackle this using data compression. And the goal of this is to both speed up I/O, even on a fast RAID system, and to also cache more data in memory. And yeah, our algorithms need to be lightweight to minimize the overheads. We don't want, if we store cache data in memory, compressed data in memory, we don't want it to be slower than, or much slower than if we would store uncompressed data. And also, yeah, to be able to speed it up on a fast RAID system, you need very high efficiency. So this is our goal, speed up the I/O bandwidth that's available by the compression ratio of the data. However, let's look at an example. We have a 300 megs per second RAID, compression ratio of 4. This would already require a decompression bandwidth of 1.2 gigabytes per second uncompressed data generation. And that assumes 100% CPU utilization, but we also need the CPU for the query processing. So at 40% for CPU for decompression, we already need 3 gigabytes per second decompression bandwidth. And clearly, generic compression algorithms won't work for this scenario, as you can see in these example decompression speeds. Even the LZO, which is considered very fast, doesn't achieve the speeds we want. So we're going to design our algorithms for speed. That means that they are very simple. We exploit knowledge that we have in a database. The data has a specific layout. We can exploit that. Data types, they come from a certain domain, the data values, and we can exploit these things. And we're going to implement the algorithms in such a way that they minimize CPU and main memory overheads. These are key ingredients to achieve this. We are going to compress relations on a per column basis. And we decompress at small granularity directly into the CPU cache and feed it into the operator pipeline. And we're going to use very lightweight CPU efficient algorithms. Let's start with the first. So we have a column of values of a certain type. And these are split into fixed sized blocks. And we are going to classify all the values into codes or exceptions. Codes get compressed, exceptions are stored in uncompressed form, and so they occupy their original size. And clearly, the compression ratio of this scheme depends on the percentage of exceptions present. So what does the disk block layout look like? We first have a forward-growing, densely packed section of code words. These are arbitrary bit width code words for fixed B. And we have a backwards growing exception list where we store the uncompressed values, which we could not compress, non-compressed values. And what are the three algorithms? They are P4, P4 delta, and PDict. And I'll introduce them now. They are very simple. P4 encodes values as a B-bit offset from a certain base value. So values within the given range get encoded, and values outside this range become exceptions. P4 delta is similar to P4, but then on the deltas of subsequent values in a column. So we just subtract the subsequent values in this column and perform P4 on them. And this is very useful for inverted files because the inverted files often sorted on docID, and we can compress the gaps efficiently using this scheme. And there's a third one, a dictionary algorithm, where the code words represent integers into a small dictionary, which is stored in the header of a block. So then we'll come to RAM CPU cache compression. Here you see two ways to integrate compression into a database engine. On the left, you see the naive way, where you first read a compressed block from disk, then you feed it into the CPU to decompress it. The uncompressed data is written back to main memory into the buffer manager, and the buffer manager then feeds it into the operator pipeline. The disadvantage of this is that we cross the RAM CPU boundary 3 times, as you can see. And this is unnecessary in our case. And it's unnecessary memory traffic. And on the right, you see the alternative, where we read a compressed page from disk, and then immediately on demand, as soon as the operator pipeline requests a vector, we decompress it directly at the small granularity into the cache. There it gets fed into the operator pipeline, and after that it can be thrown away. We don't need to materialize the uncompressed result. Then the third is to use lightweight CPU-efficient algorithms. We need a quick recap on superscalar CPUs. You see an illustration of how a CPU works on the bottom, where we see 2 parallel CPU pipelines, where each pipeline has 3 stages. This is just a simplistic figure. In reality, we have 3 or 4 pipelines with 10 to 30 stages. And the challenge is to keep these pipelines filled. All the stages need to execute an instruction, and all the pipelines in parallel as well. But there are some dangers to this, and these are branches in program logic and dependencies between data items, so values that still need to be computed to be able to execute the next instruction. This can limit the throughput in your CPU. So we avoid branches and data dependencies. Yeah, that gets us to the design guidelines for decompression code. We implement the decompression as loops over the code words. We decompress these, and we want to avoid if then else in them, and also the data dependencies. And I'll show you soon how. Naive way to mark the positions of the exceptions within the code section is to use a specific reserved symbol for them. And this doesn't work because it requires an if then else in the decoding loop. So first, we show a code example. We unpack from the code words, which is we get inputs. We unpack them into code, which blows up the B-bit densely packed code words, so we can access them directly in memory. And then we iterate over these unpacked code words and check whether it's an exception marker or not. And according to whether it is, we decode the value or just write the raw value from the exception section at the end of the block. And as I told you, if then else, this presents control hazard, and this limits CPU throughput. And furthermore, it has a risk of branch mispredictions, which I will show you now. So we've conducted a micro benchmark, which measures decompression bandwidth as a function of the exception rate, so the percentage of exceptions present in the data. And we measured the IPC, the instructions per cycle, and the branch misprediction rate of the if then else in the body of the loop using hardware counters. Here you can see the bandwidth. At the x-axis you see the percent of exceptions present, the fraction of exceptions present in the data, and y-axis the decompression bandwidth. And you see a very interesting shape. The higher the exception rate becomes, then the decompression bandwidth goes up again. So we don't see a linear decline in the decompression bandwidth as we would expect due to the linear decline in the data size. And this is caused by the if-then-else in the body, because at 50% exception rate, it's impossible to predict, as is shown in this figure. We see the thick line is the branch misprediction rate, and the thin line is the instructions per cycle. So the branch in the body, in the loop body, clearly degrades IPC and therefore throughput. What's the alternative? The alternative is to patch the scheme. Instead of using a marker to store the exception positions to mark them, we maintain a patch list through the code word section, as illustrated here. And during decoding, we first decode just from the code words without anything fancy. We don't do an if then else, nothing. And after decoding this, we patch up we walk the linked list and patch up the exception positions with the correct values. How does this look? Well, first we have again the unpacking, which I skip now, the blowing up, and then we have the core loop, which just decodes everything from the code section, regardless whether it's an exception or not. And then in the second loop, patches up the exceptions. And the second loop should be taken considerably less often in general than the first loop, because we want to keep the exception rate actually as low as possible for compression to be effective. So what does the bandwidth look like now? We see that compared to the naive approach I showed earlier, we have a much more linear decline. We don't have this weird curved shape. And we also achieve higher speeds even while we do more work. And this is how we would expect and like it to look like. And please note that we get pretty high decoding speeds in order almost 2 gigabytes per second. This is 32-bit integers compressed into 8-bit code words. And now the IPC and branch miss rate again. The branch miss rate is the thick line. We see that we hardly have any in the patching scheme, and therefore the IPC curves remain quite flat, which are the thin lines. And as I said, by doing more work, we added a second loop. We actually obtain a significant speed up. And let me show the effect of compression now. In the demo, we're going to use a second query to avoid main memory caching. And first, without compression, we get an execution time of 384. This is I/O based. It's not in memory yet. And then using compression, we speed it up to 220, which is quite a speed up, given that we have a 350 megabyte per second rate. And then to show that the overhead is very small, we're going to execute it in memory again. We see 46 without compression, and with compression, it's 53. So we have an overhead of 7 milliseconds, which is still considerable. And in the right, in the profiling graph, you can again see in the column scans that we really only need a few cycles to decompress a tuple. So we used our X100 system to participate in the TeraByte TREC. As I already mentioned, it's almost half a terabyte. We constructed an inverted file index on this, and which we compressed from using P4 and P4 delta from 28 to 9 gigabyte. And we performed 100,000 keyword searches as was required by the task. And one optimization, an optimization we did in the executional logic is, you saw the plans, they contain the merge join, but this actually conducts a Boolean end of the keywords, and sometimes this is too restrictive. So we first execute the plan with a merge join, Boolean end, and if this does not return enough results to satisfy our query, the top n, then we execute the second stage where we use a merge outer join instead of the merge join, and this will result in a disjunctive search. So Boolean OR of the keywords. But the disadvantage of the merge outer join is that it blows up the result significantly, and therefore it's slower. So as long as we can do with the merge join, we do that. Furthermore, we distributed our execution over 8 cluster nodes or 8 desktop machines, dual core machines, just partitioning the document collection in 8 partitions using a simple round robin partitioning scheme, and a centralized broker to coordinate the query execution, which is quite simple to do and illustrated here. There's an incoming query to the broker. The broker broadcasts it to all the nodes. The nodes execute the query against their own inverted index, return their local top ends, and the broker merges it into a global top end and returns the results. We ran the TeraByte TREC on the following hardware platforms, or actually on more than these, but these are not shown in the results I will present. And please take a while to read the result, to read the machines. And the results of these were as follows compared to the other systems in the TeraByte TREC. We see that throughput-wise, we do reasonably compared to the custom IR engines, but it has to be mentioned that all the other systems, they prune their index actually, and we process the full inverted file here. If we would prune as well, we could become considerably faster. But as you can also see in the precision at 20, precision of the top 20 results, you can see that this pruning very often also results in a loss of precision. So that concludes my talk and demo. I hope I have shown that large-scale information retrieval on the DBMS is feasible, and that the key ingredients to make this feasible are compression and CPU efficiency in the form of vectorized execution. And we believe that the database, a relational database environment provides a flexible environment for an IR researcher to play with models, and therefore could speed up IR research. That's it. Thank you. Any questions?
Yeah. So this is a publicly recorded talk, so keep that in mind if asking questions. So any questions?
Is X100 going to be materialized as either a product or open source?
The question is whether X100 will be materialized as a product or open source. The answer is yes, we're definitely going for that. In which form, we don't know yet. Open source would be fine with us, but if one day there would be an opportunity to go commercial, that might also be, we didn't decide on this yet, but until now it's just a research system. We're only with a few people, and we'll see where it will end, but for sure we will continue with it.
Okay, any more questions? All right, thank you very much for coming.
Thank you.